I'll talk about the quiz in a minute, but just I need to keep moving because I want to finish up chapter 16 and part of chapter 17 today. But anyway, there are different ways to express the composition of a solution. Percent by mass is one, another is molarity. And molarity is by far the most common way. Yeah. It's molarity is moles of solute per liter of solution. Thank you. Yeah, thanks. All right. The looks like for the quiz, most people got the answer. What? 178. 178. What was it? This is when you have a problem like this. You know, whenever you're given two reactants, amounts of two reactants, automatically you have to think limiting reagent. And we're given 125 liters of methane and 1,150 liters of air. So there's going to be we don't know which one is in excess, which one's limiting. So we have to show a calculation, and you have to show a calculation too. So if you're given, if we're only given methane, let's say 125 liters of methane, then we can assume that's the limiting reactant. The other one's in excess, right? But here we're given both, so we need to calculate it. So you have to show me the calculation. But which one was the limiting reactant? Air. Air was the limiting reactant because of the, air is not pure oxygen. Air is going to contain only 21% oxygen. Get down. And then we end up calculating. The other tricky thing on this particular problem is it wasn't a simple volume to volume, liter to liter conversion because water is not a gas. You know, under these conditions, 25 degrees C in 1 atmosphere, what state is water? A liquid. So you can't do it. So you had to do the full stoichiometry. All right, were there any questions on this one?
So was 178 the right answer?
178. How many sig figs does this problem officially have? 3. Well, 3, except for this one. This is only good to 2 sig figs. But that's
answer to the problem.
Yeah, the final answer should really be 2 sig figs, so it should be like 180 would be the final answer. But the percent oxygen in
Was that for class or personal?
that was for a supersaturated solution.
Did we see something now?
You did?
That was a video that we watched yesterday. This is for dry air, and so it depends on the humidity. The humidity level will change the percentage. But if we're dealing with dry air, then the percent oxygen is 20.95% to 4 sig figs. If we're dealing with humid air, it's going to change. But
Is it more humid?
if there's humidity, then this percentage goes down. But anyway, this one, this is good to 4. To 3 sig figs, what would it be? 21.0. The 2 sig figs is going to be 21, and then to 1 sig fig it would be 20. So usually I just do it 1 sig fig, 20% oxygen, 80% nitrogen. Why do I do 1 sig fig? It's just easy to remember. 80% nitrogen, 20% oxygen. But if you want to be more precise, you could say 21% oxygen, 78% nitrogen, 1% other stuff. Other stuff being argon, CO2, So officially only 2 sig figs were allowed in the final answer for that. All right, going back to this, molarity is the moles of solute per liter of solution. It's the definition. This is by far the most common because this is really useful for stoichiometry. What we can do is we can go from liters of solution straight to moles of pure solute. And so this is the best unit for stoichiometry compared to percent by mass. Percent by mass isn't so easy for doing stoichiometric calculations, especially since the heart of the stoichiometry is mole-to-mole conversion. We can go straight to moles. So molarity, even though it's a strange unit, is the most useful unit to use. All right, so calculate the molarity. Did we do this one? Calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting it to 100 milliliters, 3 sig figs. We didn't do it? Okay. So we wanted to calculate the molarity of the sodium hydroxide. Molarity of sodium hydroxide is, the number of moles of pure sodium hydroxide per liter of sodium hydroxide solution. So the moles of sodium hydroxide, we're going to just do a gram to mole conversion. So the top part here, we're just going to go from 15 grams of sodium hydroxide, that's pure sodium hydroxide. And then we need the molar mass of sodium hydroxide. The molar mass of sodium hydroxide, a mole of this weighs 40 grams, so 40.00 grams, 4 sig figs. And so we just do a gram to mole conversion, then we can get the moles on the top. And then what we're going to do is we're going to do a milliliter to liter conversion here. So we have 100 milliliters of sodium hydroxide solution. We have 100 to 3 sig figs. That's why they wrote it in scientific notation. And so we're just going to convert it from milliliters to liters using the conversion factor here. 1 liter is equivalent to 1,000 milliliters. And then just plug the numbers in. So they get 0.38 moles. Here, your book does this all the time. Your book does what we call intermediate round off. Intermediate round off, we shouldn't round an intermediate answer because that's not our final answer. Our final answer is we're going to plug that number in up here and then calculate this. And so what we should do with an intermediate answer is carry extra digits here, or don't clear it from your calculator, just leave it in your calculator. That way we don't do intermediate rounding. And intermediate rounding, let's say you have a very, very long calculation, and if you're rounding it after each step, by the time you get to the end, your answer could be significantly off.
How would you know to show the right answer? Because you don't always have the significant figures.
Yeah, so here, let's just do this calculation. Maybe it comes right on 0.38. So if I do this calculation here, I'm going to get 15 divided by 40. And the answer I get is not 0.38. The answer I get is 0.375. And so to keep track of sig figs, I do it this way. I go 0.37 and then subscript the 5, like this. Let's say, as an example, let's say you owe somebody $1.50 a day, right? So if you owe them $1.50 a day, they say, oh, let's just round it to $2. Do you want to round it to $2 every day for a year? No, because by the end you're going to end up paying a lot more than you should have if they just did $1.50 all the way to the very end. Well, that's the same kind of thing here. If we keep rounding it like this, and we call this an intermediate rounding step, then it's going to impact your final answer, and your final answer is going to be rounded once again because in And so the more rounding, it's like a domino effect. The more rounding, the further off you're going to be.
How do you stop? Do you let it go infinitely? I mean, is there a stopping point where you know?
Well, what we do is we always carry one digit more than what you're allowed. And so, for example, here,
During the math.
I'm allowed 2 because 15 has 2, 40.00 has 4. So I'm allowed 2 here. If I'm allowed 2, I carry 1 extra. That's going to be the best compromise between speed and accuracy. You know? Yeah, so you stop it there. If you just write down 1 more than you're allowed, and that's usually enough. Sometimes it depends on the calculation. You can go 2 more, but there's very little benefit in going, let's say, 3 more versus 4 more. It doesn't make much difference. But the difference between, let's say, 1 and none is significant. So this comes out to 0.375 moles here of sodium hydroxide. And so what I end up getting is this divided by 100 milliliters, which comes out to 0.1000. So I'm going to write 0.375 moles of sodium hydroxide divided by, divided by 1,000, it comes out to 0.100 liters, which is going to give me 3.75 molar sodium hydroxide. In this case, I'm only allowed 2 sig figs, so this comes out to 3.8 molar sodium hydroxide. Well, even with their intermediate rounding step, they end up getting the same thing. They're going to get 3.8 molar, but it's not always the case. Sometimes their answer is going to be off from what your answer is. I'm not sure why the book does this, because when you get to Chem 1A, that's one of the things they say is you're only allowed 1 rounding step. But in Chem 4, they're just doing rounding step upon rounding step. And, I don't particularly like doing it. Okay, so molarity is one. Now, once we have molarity, then it's a very nice conversion factor, because this is 3.8 capital M NaOH. We call this 3.8 molar sodium hydroxide, which means 3.8 moles of pure sodium hydroxide per liter of sodium hydroxide solution. So if we know how many liters of sodium hydroxide solution we use, we know exactly how many moles of sodium hydroxide we use, pure sodium hydroxide. And so molarity can do 2 things. It can convert liters to moles, or it can convert moles to liters. So we use it both ways in stoichiometry. So molarity. Molality is not as common. Molality with a little m versus the big M is defined as moles of solute per kilogram of solvent. So mostly we're dealing with aqueous solutions. So moles of solute per kilogram of water. Moles of solute per liter of water. Kilogram of water is a liter. And so this is how many moles we can put in a liter. But the difference is it's not a liter of solution. This is a liter of solution. It's a liter of water, pure water. And so when we add that solute to a liter of water, it's going to increase the volume. So the volume is actually more than a liter here for this.
Is it something that we should know?
No, not really. Molality is something you don't really need to know. We'll take a look at it here. How many grams of potassium chloride must be dissolved in 2.50 times 10 squared, 250 grams of water to make 0.400 molal solution? 0.400 molal solution. So what is 0.400 molal? 0.400 molal is 0.400 moles of solute. In this case, the solute is potassium chloride. So 0.400 moles of pure potassium chloride per kilogram of water. H2O. Kilogram of water is a liter of water. So if I had a liter of water, I would dissolve 0.400 moles in that, and I'd get that. A kilogram is also 1,000 grams. And so 250 is a quarter of a kilogram. And so I'll need 1/4. of that, which is 0.100 moles. So I need 0.100 moles of KCl. .100 times 74.55 grams per mole gives me 7.455. So I need 7.46. This calculation you don't have to worry about. Molality calculation you don't have to worry about. Percent, yes. Molarity, yes. Molarity is the most common. Molality, not so much. Normality, 0. Normality, we're going to skip that entirely. If you're doing a lot of titrations, then you'd be familiar with normality, but we don't, so we're going to skip this. And so molarity is the most important in this chapter. Percentage we've done before, it's important, but not as common as molarity. And molality is kind of rare. Normality we're not going to use at all. Molality, though, is used for something called collision process, which we'll talk about later. All right, let's switch gears here. When we buy solutions, you can buy concentrated solutions or you can buy dilute solutions. Typically, when we buy solutions, we buy concentrated solutions, so high molarity, high percentage, whatever, rather than dilute stuff. So the acetic acid you can buy at the store is vinegar. It's about 5% by mass acetic acid. The acetic acid we get here is glacial, and it's almost pure. Fine. The HCl we get here is quite concentrated. And then what we do is we buy the chemicals concentrated because that's the cheapest way, and then dilute it to our needs. And so the next section here talks about solution dilution. Solution dilution is what you do in lab quite a lot, because what we have are the concentrated chemicals, and we need to dilute them. And the equation we use is this one. The volume of the concentrated times the molarity of the concentrated is equal to the volume of the dilute times the molarity of the dilute. And so volume times molarity, in other words, liters times molarity gives us moles. So this is the moles of solute. This is the moles of solute. So we don't change the moles of solute. The moles stay the same. We just change the amount of solvent. That can be seen here. So the solute's yellow. 1, 2, 3, 4, 5. So we have 5 yellow solute particles. And then what we do is we do solution dilution. We add more solvent. And so now these 5 are dispersed in a much larger volume. So it's been diluted. How much has it been diluted? Well, what we're interested in is the molarity of the dilute. The molarity of the dilute is equal to the volume of the concentrated over the volume of the dilute times the molarity of the concentrated. The volume of the concentrated over the volume of the dilute, this is called the dilution factor. Dilution factor. And so we look at the volume of the concentrated. Well, this is the volume of the concentrated. We'll call it 1 part. Then we'll look at the volume of the dilute. If you look at the dilute, how many parts did we go to? So 1 part, 2 parts, 3 parts. Do you see that? So this looks to be a 1 to 3 dilution. So in this particular example, our dilution factor is we took 1 part of the concentrated and diluted it to 1, 2, 3 parts. Do you see that? And so we call this a 1 to 3 dilution. A 1 to 3 dilution means that we're going to have 1/3 the original concentration. And so this is a 1 to 3 dilution, so our concentration should be 1/3 of the original concentration, whatever that concentration
Is that after you dilute it?
I'm sorry?
After you dilute the small amount into the larger container?
Yeah.
Meaning 1/3 or 2/3?
Yeah, you could do whatever,
Don't look at addition.
We just look at the beginning volume and the final volume and let's see. In this case, it's a 1 to 3 because the final volume looks like to be 3 times initial. But we could do a 1 to 2 dilution. A 1 to 2 dilution would be 1 part of concentrated plus 1 part water. And so you get 2 parts total. So 1 to 2 dilution. A 1 to 2 dilution would have a dilution factor of 1/2 and cut the concentration in half. Let's see if you can tell what this solution is. These are expensive flasks here. Do you know what these flasks are called? These are called volumetric flasks. Volumetric flasks are high precision glassware. And they have these very long necks. They have these very long necks because what happens is when you make these, you can't make them exactly the same. No two volumetric flasks are exactly the same. You know, because they just blow on the glass. And so what happens is, since they can't make them exactly the same, the bulb down here, what they'll do is they'll put a long neck here, and it fills it up with 1,000.00 milliliters of fluid, and then they etch a line in the neck. So some of these have a line down here because the bulb is a little bigger. Some of these have a line up here because the bulb is a little smaller. And so there's fluctuations in the bulb size. That's why they have to have such a long neck here. And so this is the mark. You look for the mark. And so what we have is we have 100 milliliters concentrated here. Okay, so what they're going to do is they're going to do this. They're going to do 100 to 1,000. This is a 1,000 milliliter volumetric flask. To do a 100 to 1,000 dilution, what they'll do is they'll take all of this 100 milliliters and pour it into the 1,000 milliliter flask, like that. But it's hard to get all of it, and so so if you look here, what are they doing? It's hard to get all of it because some of that residue sticks to the inside of this small 100 milliliter volumetric flask. So they rinse off the remaining concentrated solution and then pour it in here. And so they get rid of, if you look here, they pretty well rinsed all of it into here. Okay, once they rinse it all in here, it fills about this much of this flask. And then they fill the rest with water. And then there's going to be a line etched here. The line's etched way up here. You can barely see it. But they're going to fill it right to the line. When they fill it right to the line, then that's 1,000.00 milliliters worth volume. And so in this particular example, we start off with 100 milliliters concentrated. But we're using this volumetric glassware. This volumetric glassware allows us to get 2 more decimal places. So it's 100.00 milliliters of concentrated stuff. And then we're going to dilute it to 1,000. And again, this is volumetric glassware, so we're going to get 2 more decimal places. So it's 1,000.00. And so in other words, it's a 1 to 10 dilution to 4 sig figs. Do you see that? A 1 to 10 dilution to 4 sig figs. And so here's the diluted stuff here. So what the original concentration is the original concentration is 0.100 molar. The concentrated stuff isn't very concentrated. It's 0.100 molar, but this is potassium dichromate. So potassium dichromate is pretty reactive. So 0.100 molar is pretty well concentrated. You can see by the color there. Then you do a 1 to 10 dilution, so you'll end up with 1/10 the concentration. So this is a 1 to 10 dilution of 0.100 molar. So I have 5 sig figs here, 6 sig figs here, 3 sig figs here, so I'm only allowed 3 sig figs in my final answer, so it's going to be 0.100 molar potassium dichromate. Here. Or 100 to 1,000 dilution. So that's solution. You buy the concentrated stuff and then you just dilute it to what you need. So we could do a calculation here. How many milliliters of commercial hydrochloric acid, which is 11.6 molar, should you use to prepare 5.50 liters of 0.500 molar hydrochloric acid? And so they're asking us not for the concentration, they're asking us for the volume in this particular problem. So let's figure out what we have. So they give us the molarity of the concentrated, they give us the molarity of the dilute, they give us the volume of the dilute. And so what's missing is the volume of the concentrated. So the volume of the concentrated is going to equal the molarity of the dilute over the molarity of the concentrated times the volume of the dilute. And so plugging in the molarity of the dilute is 0.500 molar. The molarity of the concentrated is 11.6 molar. The volume of the dilute is 5.50 liters. So what does that come out to? It comes out to 0.237 liters of the concentrated, which is going to be 237 milliliters of concentrated. And so in this particular example, we have to take 237 milliliters of concentrated and then add lots of water. We've got to add lots of water until the volume gets to 5.5 liters. What we're going to do. So that's solution dilution. This is a very useful equation for lab. Then we're going to switch gears again. We're going to go from solution dilution to stoichiometry. Solution stoichiometry. For solution stoichiometry, we want to use the molarity. So calculate the volume in milliliters of 0.842 molar sodium hydroxide required to precipitate as copper 2 hydroxide, all of the copper ions, and 30.0 milliliters of copper 2 sulfate. And so what's the reaction here? It's going to be the reaction between copper 2 sulfate and sodium hydroxide. So what's the formula for copper 2 sulfate? CuSO4. Aqueous. Plus sodium hydroxide, NaOH. This is going to produce copper 2 hydroxide, CuOH2, and what else? Yeah, plus NaSO4. Does that look right? Yeah, Na2SO4. Now that's right. Yeah, 2 in front of the NaOH. Good. Okay, so what our given is we were given 30 milliliters of copper 2 sulfate solution. So over here, we'll just start off with 30.0 milliliters of CuSO4 solution. We also know the molarity of the copper 2 sulfate solution. The molarity is, write it up here, 0.635 mole of pure copper 2 sulfate per liter of copper 2 sulfate solution. So if we know how many liters of copper 2 sulfate solution, then we can figure out how many moles we have by using molarity. And so the first step I'm going to do here is convert milliliters to liters. All right, so we'll just do this using dimensional analysis. 30.0 milliliters of CuSO4 solution. And then a liter is equivalent to 1,000 milliliters. Milliliters cancel milliliters, and that leaves us with liters of CuSO4 solution. Well, if we have liters of CuSO4 solution, we can get the moles using the molarity. So let's do that next. 0.635 moles of CuSO4 per liter of CuSO4 solution. So we're going to get rid of the solution and now figure out how many moles of pure CuSO4 we have. So we're going to go from liters to moles of CuSO4. Well, once we have moles of CuSO4, then we can just do a mole-to-mole conversion. We get moles of NaOH. Looking at the mole ratio, it's a 2-to-1 mole ratio. So 2 moles of NaOH per 1 mole of CuSO4. So moles of CuSO4 cancel. The pairs here cancel. It gives us moles of NaOH. But if we have moles of NaOH in the molarity, then we can get the liters. 0.842 molar sodium hydroxide. So 0.842 moles of pure sodium hydroxide per liter of sodium hydroxide solution. And so here we can go from moles of pure sodium hydroxide to liters of sodium hydroxide solution. So I'm going to tack on another conversion factor here. The conversion factor is 1 liter of sodium hydroxide solution contains 0.842 moles of sodium hydroxide, pure sodium hydroxide. So moles of pure sodium hydroxide cancel. That leaves me with liters of sodium hydroxide solution, and they want milliliters. So I'll just do a milliliter conversion here. 1,000 milliliters per liter. Let's see what that gives us. Your book likes to do this. Rather than saying 0.635 moles per liter, they go per 1,000 milliliters. So okay. But I'm so used to moles per liter. I'd rather take an extra step, so I don't have to do it this way. 45.2 milliliters of sodium hydroxide. So we should be allowed 3 sig figs at the end. 45.2 of sodium hydroxide solution. Then your book also does this. They don't distinguish. People get confused. Is that milliliters of pure sodium hydroxide or milliliters of sodium hydroxide solution? And so in Chem 1A, students always get confused. For example, I asked them milliliters of pure. If I ask you milliliters of pure sodium hydroxide, you're thinking I need the density of the sodium hydroxide. It's a solid. You gotta figure it out. Versus milliliters of sodium hydroxide solution. Well, that's different. And so even in Chem 1A, students get confused. So I like to label things differently. Because here, when they do this, it confuses even Chem 1A students. 0.635 moles of pure copper 2 sulfate per 1,000 milliliters of pure copper 2 sulfate? No, this doesn't make sense at all.
So in order for it to make sense, each element has to be soluble.
Well, in order for it to make sense, complete sense, so you don't get tripped up, you should make sure you label it as detailed and descriptively as possible. And so when somebody says 45.2 milliliters of sodium hydroxide, I'm wondering, are they talking about solid, pure sodium hydroxide? Or are they talking about solution? This isn't labeled with enough detail for me. So it should be labeled more. That's another thing. This book, because the way the book does, and I understand why the book does it like this, because they don't want to go into too much detail. But if you don't, then you get into bad habits when you get into more difficult problems. And you have to, when you do these types of things, you have to make sure that they cancel out in a logical fashion like this. Any kind of problem that you do, you have to add these things, and these things have to be valid in itself. This is why I don't like to do it this way. I don't like to do 0.635 moles per 1,000 milliliters, even though it's correct, because I can look at this and go, okay, this is valid because it's 0.635 molar, and so that's 0.635 moles per liter. Versus this, when I look at this, it doesn't shout molarity to me, and so it's harder to see. But you got to make sure that things line up in this fashion. Well, anyway, it's time for a break, so let me stop here. Take a break.